Hi, in this video we're going to show you how to teach division of fractions for the first time. So to do this I've broken this into 4 parts. So part 1 is the big idea, so what we want our students to walk away with, the main concepts that we want them to understand in order to take division of fractions further. Part 2 is the prerequisites, so things that we might want to consider checking that our students understand before we begin to teach the topic. Part 3 is how we're going to teach division of fractions, or how I teach division of fractions. And part 4 is all about making connections, so where this links to other areas in Key Stage 3 and Key Stage 4.
The first big idea is building on students' conceptual understanding of division. This lies between 2 main strategies. So we have grouping or quotative division, and we also have sharing or partitive division. So both of these strategies are taught before Key Stage 3. However, for dividing fractions, we need our students to be thinking about grouping when they divide. Otherwise, the whole concept kind of falls apart, particularly when we start dividing by numbers which aren't integers. So for example, I might start this by just simply asking a group of students, how do I calculate 12 divided by 3? Any students that are thinking of sharing, they might suggest taking 12 things and then splitting those 12 things into 3 equal groups. So that would be sharing. So the 3 equal groups would each have 4 in, hence the answer would be 4. Now what we want students to be thinking about is grouping instead. So instead of thinking about taking 12 and splitting it into 3 equal pieces, we're going to think about the number 12, and we're going to think about how many times we can physically fit groups of 3 into 12. So if we do it this way, we will end up with 4 groups of 3, and again revealing that the answer must be 4.
So presenting a problem like this at the start of the topic, or even before the topic, is something maybe to get the students to really think carefully about the concept that we're trying to get them to hold on to. So what we want them to be thinking about in terms of their calculating for this is ideally thinking about how many times 1/10 will physically fit into 1/2. That's the crux of the problem, and that's what we want them to think about, and hopefully what we'll be encouraging them to think about when we move forward. And this is a similar problem, just with a different representation. So this time we've used a bar model, but again, it's instilling that idea. So we want students to really realise that if they're being asked to take 2 and divide it by 1/3, what we want to know is how many times 1/3 fits into the whole number 2. So as soon as we start dividing by numbers which aren't integers, the concept of sharing kind of loses its value there. So it's really important that we think about this idea of grouping to move forward. One of the main misconceptions we might meet is where students will often think that dividing will always make numbers smaller. So it's important that we point this out to them that this isn't always the case. So one way to do that is to follow a simple pattern like this one. So if I take 12 and divide it by 12, I get the answer 1. If I then decrease my divisor, my quotient increases. And this continues to happen as I decrease my divisor every time. So if I take 12 and divide it by 4, I get the quotient 3. If I decrease that once more, so if I decrease it to 3, so 12 divided by 3 will give me a quotient of 4. So again, the quotient has increased. So every time I decrease my divisor, my quotient increases. And then once we reach this point, so we've got 12 divided by 1 is equal to 12. Some students might think, right, okay, we can't do anything else, but we haven't restricted anything. We haven't said that we can't use numbers which aren't integers. So then I would simply pose that kind of question. And what kind of thoughts are going through their heads? So even if they can't give me the correct answer, can they see that the answer would have to be larger than 12? Because it would have to increase. We've decreased the divisor again, so there's no reason at all why the quotient shouldn't be increasing in this case. To further embed this idea, you might want to present a problem similar to this one. So again, just introducing a little bit of reasoning. So what we want students to latch onto again is the fact that if we increase the divisor, then the quotient will decrease. So in the first example, on the left we have 12 divided by 3, and on the right we have 12 divided by 4. So the calculation on the right, because the divisor is larger, that means that this value is going to be smaller. So therefore that would be the correct statement, or the correct symbol, sorry, to complete this statement. If I look at the next one, very similar again. So I've got 12 divided by 15. Again, this would give them a calculation where they may be not comfortable working with whole numbers this time, but they should be able to establish that because the divisor on the right is smaller than the divisor on the left. That means the calculation on the right hand side is the larger of the two. So therefore this will be the correct symbol to complete the statement and make it correct. And then likewise with the last one, similar again, we've got 5 over 7 divided by 3 over 7, and then 5 over 7 divided by 4 over 7. But again, out of the two, the larger divisor is the calculation on the right hand side. So therefore, using their reasoning skills, they should be able to complete this correctly once again.
Another of our big ideas is students realizing that they can alter or change the form of a calculation to make it more manageable. So like when we add fractions together, we know that we can make our denominators the same, and once we've achieved this, the calculation is easy to comprehend. And likewise, with dividing fractions, we know that we can multiply by the reciprocal, and this will make an equivalent value, so we can answer this calculation rather than the original calculation given.
Now moving on to part 2, as discussed in the first part, we need to make sure that students really understand and grasp this idea of grouping. So in order to understand why 5 over 6 divided by 1/6 is 5, it's often useful to maybe display this with a number line, possibly a bar model. So if we take this number line, I'm going to indicate that 5/6 is here. And what I want to know is how many times 1/6 will physically fit into 5/6. So I'm literally going to fill up this bar model until I reach 5/6. So I have 1/6, I have another one, and another, and another, and one more. So therefore my answer is 5 because 5 of those 1/6 fit into 5/6. With this one, another prerequisite that we want to just make sure that students have met before and that they understand, they have a comprehension of what's going on, is just the use of improper fractions. So a lot of the time when we divide fractions, we're going to be either calculating with improper fractions or we're going to have quotients which are improper fractions. So it's important that students understand the relative concept behind them, i.e. that they are greater than 1 in value. So if we take this example again, so 7 over 3, displaying this on a bar model, I would explain that this would have to go here, so it's just over 2, so that would be equivalent to 2 and 1/3. And again, we're just simply figuring out how many times 1/3 will fit into this model. So I've got 1/3 plus another third plus another third, etc. And I know altogether that that will give me a value of 7 because 7 lots of my 1/3 will fit into my 7/3. Now, get the elephant out of the room. You may meet some students who can already successfully divide fractions, and they may use one of these 3 methods. So lots of the time students might get told to use the KFC method, which stands for keep, flip, change. So you keep the first fraction the same, you flip the second fraction, then you change the sign. Or they might get told to flip it and times it, or turn it upside down and multiply. Anything along these lines. It does lead to a successful answer at the end, but this is simply teaching a procedure. And what we want our students to understand is the mechanics behind this, and more importantly, why it's working, so that they can be more successful with more abstract concepts linked to this topic. Right, now the first job is to make sure that my students understand what a reciprocal is. So with this task, what I would ask students to do is to choose a number from the first list and a number from the second list, with the goal being that those 2 numbers must have a product of 1. And what I'm hoping students will realise is that when the relationship between these two, so for example I want them to spot that 9 multiplied by 1/9 will give them a value of 1, and therefore 1/9 and 9 are reciprocals of one another. Or if I multiply 7/5 by 5/7, that will also give me a value of 1, as it will give me a value of 35 over 35. So I want them to be able to pick this out and realise the relationship between these two, particularly the link between 5/7 and 7/5. Now before I start dividing fractions, what I might present my students with is a simple problem like this one. So I'm going to ask my students to simplify this fraction. Now what I don't think will happen very often is that they will spot that 18 is the highest common factor of 18 and 126. I feel like with a problem like this one, a lot of students will work in steps. So I think the first step might be they're both even numbers, so I can divide them both by 2. So I get an equivalent fraction of 63 over 9, which is still correct. That's fine. I can't divide both of these by 2 anymore, but I can divide them by 3. And if I look carefully, I can divide that by 3 again, so I get 7 over 1, so that gives me a value of 7. Now, once I've completed this task, what I want students to realise is that they've also been looking at this idea. So if 126 divided by 18 is equal to 7, then 63 divided by 9 is also equal to 7. So we're thinking about the fractions as calculations. We're pulling that link together. So we're saying that 126 over 18 is equivalent to the calculation 126 divided by 18, or it's equivalent to the calculation 63 divided by 9. We also know that 21 divided by 3 is equal to 7. And we also know that 7 divided by 1 is equal to 7. Right? This is a key idea when we move further forward. Now, moving forward with this, if we want students to solve the problem on the left-hand side, so 5 divided by a half, what we want them to think about is, on the previous slide, our calculation was really easy when we were dividing by 1. So if we can change this calculation to an equivalent calculation, where we divide by 1, then we can answer our question really easily. So all we need to do is to figure out how to make the divisor equal to 1. But with all the previous work that we just did on reciprocals, that should be nice and straightforward. So all we would ask is, what would I multiply 1/2 by to get the value of 1? And hopefully at this stage, students will acknowledge that they can multiply by the reciprocal. So if we multiply 5 and a half by 2, which is the reciprocal of a half, we get a new calculation, which is 10 divided by 1. And 10 divided by 1 is equal to 10, which is the solution to the problem. If I look at the calculation on the right hand side, similarly again, what I want to do, I want to make this calculation and I want to change it to an equivalent calculation where the divisor is equal to 1. So to make the divisor equal to 1, I would have to multiply by 1/3 by the reciprocal, which is 3. But I need to make sure that I do that to the dividend as well. So if I multiply both by 3, I will get a calculation of 15 divided by 1, or the answer 15, which is the answer to the problem, 5 divided by 1/3. After students have practiced that concept, I'd then move on to the next stage. So far I've got my students comfortable with dividing by unitary fractions, and now it's time to look at what happens when we divide by non-unitary fractions. So the example on the right, I want students to acknowledge that the numerator is not 1, and in this case is 2. And I also want students to acknowledge that the calculation at the end has been left as 15 divided by 2. And then we're going to look at how that's going to change things moving forward.
At this point, I'm going to emphasize that I need a calculation equivalent with a divisor equal to 1. So at the moment, my divisor is equal to 2, and I would simply ask students what I need to do to create a calculation that is equivalent with a divisor equal to 1. And hopefully they'll be able to tell me that they're going to need to divide by 2 to achieve this. So once I've done this, I end up with a calculation of 15 over 2 divided by 1, which is obviously equivalent to 15 over 2 because I'm dividing by 1. After this, I will give the following prompts. So what calculations did we do to get from 5 divided by 2 over 3 to 15 divided by 2? So the 15 divided by 2 is equivalent to our fraction 15 over 2. So I want students to really think about the calculations that took place at this stage. So we can see that we've multiplied by 3 and we've divided by 2. Then I would ask students to complete this information. So 3 divided by 2 is equal to 3 over 2. So we're pulling this link in together about the fact that the calculation, a division, is equal to a fraction. So 3 divided by 2 is equal to 3 over 2. I then ask them to complete this statement. So if I've taken 5, multiplied it by 3, then divided it by 2, that's the same as 5 multiplied by 3 over 2. So we've shown that our calculation 5 divided by 2 over 3 is actually equivalent to 5 multiplied by 3 over 2, or the reciprocal.
Now to move forward, all we need to make clear to students is that every time they divide by a fraction, they can create an equivalent calculation. So 5 divided by 2/3 is the same as 5 multiplied by its reciprocal. 7 divided by 2/3 is equal to 7 multiplied by its reciprocal. 7 divided by 3 over 2 is equal to 7 multiplied by 2 over 3, which is the reciprocal of the original divisor. And 2/7 divided by 3 over 2 is equivalent to 2/7 multiplied by 2/3. At this stage, I would consider introducing students to examples where both of our fractions have the same denominator. Now, we looked at this earlier, but the difference was that the divisor was a unitary fraction. So, for example, 5/7 divided by 1/7 would give us a value of 5. Now, the concept of 5/7 divided by 2/7 is slightly different. So, if we take a similar approach and I highlight 5/7, what I want to know is how many times 2/7 will fit into 5/7. So 2/7 will fit in once, twice, and it will fit in another half times. So that means that this is equal to 2.5, and if we convert this into an improper fraction, this will give us 5 over 2. Now there is a link that we can establish when we have our denominators the same, and that is that if we divide our two numerators, we get the solution to the problem straight away. So if we take our 5 and divide it by 2, that's equivalent to 5 over 2.
Now when I divide two fractions whose denominators are equal, there is a nice pattern which can be found. So using the same strategy, I can make this calculation equivalent to 6 over 7 multiplied by the reciprocal of 5 over 7, which is 7 over 5. And this will give me a value of 42 over 35. Now when I simplify this fraction, I need to find a factor of both 42 and 35. And this factor in this case is the number 7. So 7 is a factor of 42 and it's also a factor of 35. So this will give me a final value of 6 over 5. And if we look carefully at the original calculation, the numerators of our two fractions are 6 and 5. Now the reason for this is linked to this stage in our working, and it's also linked to how we simplified 42 over 35. So if we take this calculation circled, we know that it's equivalent to this. So 6 multiplied by 7 all over 7 multiplied by 5. Now that must mean that this is also true. So 6 multiplied by 7, which is our 42, all divided by 5 multiplied by 7, which is our 35. And if we look at this closely, that must mean that this is also true. So 6 over 5 multiplied by 7 over 7. And we should know that 7 over 7 is equivalent to 1. So we've multiplied 6 over 5 by 1, which gave us our answer of 6 over 5.
After this, I then see if students can spot the pattern. So 6 over 7 divided by 5 over 7 is equal to 6 over 5. If I change the denominators, I still get a value of 6 over 5. So I'm still calculating 6 divided by 5. If I change the numerators, I get a new divisor of 7, so 6 over 7. So changing the numerator of the divisor will give us a new denominator of 7. And if I take 7 over 11 and divide it by 6 over 11, so I've changed the numerators, that will give me a value of 7 over 6. And at this stage, you might want to leave this for students to digest and then ask them what patterns they've discovered. So have they realised that they can just divide their numerators when their denominators are equivalent?
Once I feel my students are confident, I would like to give them a set of questions similar to this, so a bit of intelligent practice. So if I look at the first example, my denominators are the same and I have 6 and 5 as my numerators, so I'm going to get a value of 6 over 5 for this question. The next one I'd ask students to think about what's changed. So the only thing that's changed is the numerator of the second fraction. and that's going to impact the answer by changing the denominator of my solution. When I change the denominators, this has no impact on the answer at all, so the answer remains the same. That's another discussion point that you might have with students. What would happen if we had 6 over 1 million divided by 7 over 1 million? The answer would still be 6 over 7. If I reverse the order of my numerators, this changes the fraction again. So this time the numerator is 7 and the denominator is 6. We can also get integer solutions in some cases. So we have 12 divided by 6, and this will simplify to give me 2 wholes. And we can also generalize algebraically. So a over 17 divided by b over 17 must be equal to a over b.
Taking this a step further, I'd want students to also realise that they can manipulate questions so that their denominators are the same, which might be a strategy that they like to use in order to answer questions. So for example, the main difference between these two questions is that the second question has 2 different denominators, whereas the first question has 2 denominators which are equal to each other. So the first question we should be able to get an answer out nice and easy, which is 6 over 5. Whereas the second question, to access the second question, we would need to make our denominators equivalent first and then move forward from there. So we get a solution of 12 over 5 for this question. After some fluency in both of these methods, I'd want my students to be able to decide which is going to be more efficient depending on the problem that's being presented to them. So are they going to multiply by a reciprocal every single time? Or are they going to make their denominators the same and then divide their numerators every single time? Or is there scope for them to maybe dip in and out of both methods depending which one is more efficient given the problem that they face? So the first example, we have 17 over 12 divided by 37 over 8. And what we want to present to students is what will happen when we use both methods. So for example, if we multiply with a reciprocal, we get 17 over 12 multiplied by 8 over 37. And this would mean calculating 17 multiplied by 8 and 12 multiplied by 37. Now, whilst this isn't impossible, it might take some time, and obviously it opens students up to potentially making some slight errors in their calculations or their algorithms. So if we have 136 over 444, we're going to need to simplify that as well. And again, it might be difficult to spot the highest common factor straight away, so we could start by halving both of these, as 2 is a factor of both, and then do this again, so we get 34 over 111. Or if we make our denominators the same, so if we get 2 denominators of 24, as it's the highest common factor of 12 and 8, we get a numerator of 34 and a numerator of 111, but as our denominators are the same, we know that our answer is going to be 34 over 111. So given this example, we could argue that making our denominators the same and then dividing our numerators is the most efficient way to solve this problem. But we want students to be able to make this decision based on other questions that they may face. Now, in order to build some fluency within the topic, I'd want my students to attempt a task similar to this one. So the goal with this is not necessarily just to find the solutions, although this will be the ultimate goal. The actual thing that I want to get out of this is an understanding of why students may choose a certain method. So what kind of triggers in the question will lead students to answer a division question in a particular way. So for example, question 1, I feel like after all the pre-teaching that we've been through, I feel like lots of students could comfortably tell us that the answer is 2 over 3 and probably wouldn't opt to multiply by a reciprocal. For question 2, we've got some larger numbers, so this one could be up for discussion. So yes, we can make our denominators the same. Is that going to create more work than if we just multiply by the reciprocal? That's a question which could be posed to the class and have a discussion about. Question 3, so could students make our denominators the same, so they could find a common denominator of 15 and then get their answer possibly through simplifying? Will students acknowledge that they can simplify 12 over 15 at the start, which will give you 4 over 5,
and make the problem very similar to question 1 once we've manipulated it in this way. And question 4, is it easier to create 2 equivalent fractions and then divide the numerators, or is it easier to multiply by the reciprocal for this one? The numbers are quite manageable, so that could be a discussion that is had. But again, these discussions are things that I want my students to be having in order to decide which method they're going to use to solve the problem. So making connections with this topic and other areas of Key Stage 3 and Key Stage 4, we can reinforce links between calculations and fractions. So we've pointed out lots of times that 12 divided by 5 is equivalent to the fraction 12 over 5. This also creates links with equivalent fractions and decimals, so students, after covering this content, might be more comfortable converting fractions to decimals, particularly improper fractions to decimals. This will also reinforce methods associated with addition and subtraction of fractions. So the main method moving forward is to create equivalent denominators so that we're dealing with the same unitary values. And obviously this method has been used in some of the examples with dividing fractions. It will also help with dividing algebraic fractions. We can rearrange and solve when we have fractional coefficients. And we can also solve ratio problems involving fractional scale factors.